Swayam Prabha. Digital India. Educated India.
Hello and welcome to Lecture 10 on Special Relativity. In today's class, we're going to discuss the notion of tensors. This will be the most general way in which we can extend our dictionary to cover all kinds of objects which transform under the transformations of special relativity, that is under rotations and Lorentz boosts. So to start off, we'll first discuss the transformations of vectors or four vectors again, but using different notation than we used last time. So rather than use matrix notation, we will switch to what is known as index notation. Now, the notation is actually going to be extremely useful when we try to understand the idea of tensors. Then we'll discuss specifically the idea of what are called contravariant and covariant indices. The one important thing is that these indices do not represent different objects, but they're just a different way of representing the same object. And then we'll talk about the ideas of dot products, which we discussed before for four vectors using matrix notation. And we'll discuss what this looks like in index notation, and we'll see it's here that the use of upper and lower indices simplifies the way in which we write down dot products. Then we'll see that it's also possible to construct a different type of product of four vectors rather than just a dot product, and this is called a tensor product. And once we understand how these tensor products transform, we can generalize this idea to conjecture other objects called tensors which transform in the same way as these tensor products. So this gives us a set of generalized objects which have transformations which are different from four vectors under Lorentz transformations. And this most general set of objects which transform in this way, these tensors, will allow us to understand the most general way in which Lorentz transformations can act on different objects. In the last class, we saw how to write the transformations for four vectors using what is called matrix notation. So in matrix notation, we took a matrix lambda, which is an element of the Lorentz group. So if we take proper orthochronous Lorentz transformations, it belongs to the set of matrices of SO plus 3, 1. So that is matrices that satisfy the property lambda transpose dot G dot lambda is G, and determinant of lambda is plus 1 rather than minus 1, and the 0, 0 component, that is the top leftmost component of lambda, was greater than or equal to 0. And we saw that if we have such a matrix lambda belonging to this Lorentz group, then we could take quantities such as four vectors, and these four vectors, to give specific examples, were things like the time and space coordinates, which we denote as the four vector x, and the combination of partial derivatives with positive sign for the time-like derivatives and negative sign for the space-like derivatives, and also a four velocity u. Okay, and these four quantities, we found that if we have an observer S and we want to go to an observer S prime and find the corresponding quantities according to observer S prime, and if we call the quantities for observer S prime as the vectors V prime, which we denote as x prime, partial prime, and u prime, then we saw that the transformation law which relates these different quantities, that is the transformation that relates x prime to x, partial prime to partial, and u prime to u, is actually very simple. So in general, for any v prime to relate it to v, the transformation rule is simply that v prime is equal to lambda dot v, where this is a matrix product. Now, this transformation rule is true for 4 vectors. So if v is a 4 vector, it transforms in this way. Now, it's not obvious what quantities transform like 4 vectors. Obviously, if we just take any 4 numbers, it's not guaranteed that they transform like 4 vectors. What we have found is that assuming that t, x, y, z transform like a 4 vector, so this is what we called x, then we could derive the dictionary or the transformation for the quantities partial, which was partial ct, minus partial x, minus partial y, and minus partial z. And we could also derive the transformation law for u, which was c, and then ux over square root of 1 minus u squared by c squared, uy over square root of 1 minus u squared by c squared, and uz over square root of 1 minus u squared over c squared, where ux is the change in the x coordinate in frame S per unit time interval in the frame S, and so on. Okay, for uy and uz. So the transformations laws for u and this quantity partial were derived from the transformation law for x, and therefore we found that partial and u also transform like 4 vectors. Okay, so it's not always true that you will be able to derive the transformation law from the transformation law for x. Okay, some things just intrinsically transform like 4 vectors, but we don't have a way to derive from first principles that this transforms like the quantity x. Okay, so in that case, you postulate that something is a 4 vector, and you start with that assumption. So it's not easy to identify 4 vectors, but once you have 4 vectors, they transform in this way. Okay, that is, given v in some reference frame S, you can go to a different reference frame v prime, where v prime is related to v through this transformation. Now, today we'll see a different way of writing the same transformation using what is called index notation. Okay. This is just a way to denote matrix multiplication using explicit indices. So supposing I have a matrix M, which is an n cross n matrix, and I have a column vector v, which is an n cross 1 matrix, then the matrix product of M with v can be written in terms of index notation as, let me identify the elements of M with M, I, J, where I runs from 1 through n and j runs from 1 through n. And let me identify the elements of v by vj, where again j runs from 1 through n. Okay, and if we sum over j, then what we get is the matrix product of M with V. Okay, and this gives us v prime, or in index notation, this is strictly speaking the ith element of v prime. So let me just move this down here. So v prime, if I take the ith entry of v prime, it's related to the matrix product in index notation in this way. Note that the only thing that we're summing is over j, where j goes from 1 to n. On both sides, I is a free index, which means we have to make a choice of what I is from the list of 1 through n. So if we think about this in terms of column vectors, so we have a column vector v prime, and the entries I so the entry I corresponds to the ith row of this matrix. And the statement is, if we want to find what v prime I is, that is this quantity, then what we need to know is in the matrix M, we need to find the ith row. So that is, we need to find the row over here. So this would be mi1, mi2, and so on till min. Then we find the corresponding vector v, and we take the entries v1, v2, v3 till vn, and we multiply mi1 by v1, mi2 by v2, and so on, and min by vn. We sum all of those together, and that would give us vi prime. Okay, so j is the second index over columns. So j is 1, 2 till n. And when we sum over all columns and multiply by the corresponding vj's, the entries in the rows of v, we get vi prime. Okay, so this is just well known from writing matrix multiplication using index notation. So similarly, we can write down for 4 vectors. So specializing now to the case n is equal to 4. We can write down for 4 vectors v prime is equal to lambda dot v in matrix notation. And we make a few small changes when using matrix notation in special relativity. So the first thing that we do is we use Greek letters for the indices. So rather than use the letters I and j, we typically use things like mu, nu, rho, and sigma. Okay, so let's start with using mu and nu. And so we'll write this as lambda mu nu v nu and v prime mu, and a sum over nu over here. So lambda was a 4 by 4 matrix. If we choose a value of mu and we choose a value of nu, we pick out a particular entry of lambda. So choosing mu in this case would be choosing a row of lambda, and choosing nu would pick out a column of lambda. Okay, and the one thing that you'll note is that the row index mu is raised over here. So we make a distinction between row indices and column indices by raising the row indices. So the mu index, which corresponds to a row, okay, a row is raised. Okay, so row indices are raised. And similarly, you see that for v, nu is the row index, right? So the index vj, the jth index the value of j corresponds to which row we're talking about. So again, we raise the row index. Okay, so in all 3 places, The index that is raised is the row index. Okay, and column indices are written as lower indices. So let me write this more specifically, okay, or with different colors so that you can clearly see. The raised indices I'm going to write in green. And the column indices I will write in a different color. I'll use white. So this is the same matrix product in index notation. Okay, so this is the second change. The row indices are raised and the column indices are lowered. Okay, and the value of mu, instead of saying it goes over 1, 2, 3, 4, we say it goes over 0, 1, 2, 3. Okay, so 0 being the time-like coordinate and 1, 2, 3 being the space-like coordinates. And similarly for nu as well. So for both mu and nu, okay, rather than saying the values go over 1, 2, 3, 4, we say they go over 0, 1, 2, 3. So 0 is our time-like coordinate. This is our x-like coordinate, and this is our y-like coordinate, and this is our z-like coordinate. Okay. Now, the third change that we will do is this sum over nu runs from 0 to 3. Okay, it runs over 0, 1, 2, 3. So the third change that we will make is we know that when we have one column index and one row index, which are the same, that is nu is the same as nu, it's like we're multiplying this row with this column. Okay, and whenever we do this, we will always be summing over nu, because in that case we will be taking a matrix product. So we will drop the summation and assume that whenever we have one lowered index and one raised index, which are the same, so the value of nu is the same as the value of nu, that means that I have to sum over nu automatically. Okay, so the third thing we will do is drop the summation, or make it implicit. Okay, that is, we don't write it down explicitly, but we assume that such a summation is being done. So we write it as v prime mu is lambda mu nu v nu. Okay, so we've just dropped the summation sign, but implicitly we're assuming that we're summing over the values of nu, where nu runs from 0, 1, 2, 3. Okay, so this is called the Einstein summation convention. Okay, which is whenever I have a repeated index, in this case nu, which is both raised and lowered, so it appears as a raised index and a lowered index, I assume that there's a summation over nu. Okay, then assume a summation. Now we'll see that the second rule that we had for raised and lowered indices is where we took row indices and raised them and column indices and lowered them. This law is going to be incompatible with law number 3. Okay, so actually what we're going to do is we're going to take law number 3 as the correct notation convention, and we'll see what this implies for the generalization of the second law of raising row indices and lowering column indices. So what we've done so far is correct, which is vector indices will be raised, and the transformation matrices will have mu and nu in this form. Okay, and the resulting summation will also result in a vector which has a raised mu over here, which is again a 4-vector index. So let's see where the conflict arises between law 2 and law 3. So the conflict will actually arise when we write down something like lambda transpose. Okay, so when we write down lambda transpose, now lambda has indices mu and nu, but now when I write down lambda transpose, what I need to do is reverse the indices. That is, if I take the ijth entry, so now I'm not going to use upper and lowered indices, but supposing I take the ijth entry of lambda transpose, this is going to correspond to lambda ji. Okay, it's the jith entry of lambda. So now if we want to take lambda transpose and we want to find the ijth entry, so now let's replace them by Greek indices. And now let's apply our rule for raising and lowering indices. So if we raise the row index for lambda and we keep the column index lowered, on the right hand side we would have this. However, for lambda transpose, what we would like is a matching of the raised and lowered indices to the indices on the right hand side. Okay, so that is raising and lowering of indices on the left hand side of this equation should match the raising and lowering on the right hand side. So if we do this, what we would need is to keep the index mu lowered but raise the index nu. Okay, so this would be an upper index and this would be a lower index. However, on the left hand side of this equation, mu is actually a row index for lambda transpose and nu is a column index. Whereas on the right hand side, nu is a row index and mu is a column index. Okay, so the rule that we prefer is this rule, okay, which is that for the transpose matrix, we match the upper and lower indices not by whether it's a row or a column, but by comparing with the indices of lambda. Okay, so this is the preferred rule. So this overrides rule 2 for something like lambda transpose. Okay, and now let's see what this implies for the metric G and the indices of the metric G. So in matrix notation, we have the rule lambda transpose dot G dot lambda is G. And now let's put in indices. So lambda transpose, let's put in just indices I and j. So let's write this as Gij. And over here we would have lambda transpose I k gkl lambda lj, okay, where I summed over the indices k and l. Now we'll drop the summation, okay, as is the Einstein summation, or actually let's drop the summation at the end so that it's clear what we're doing. So let's keep the summation over k and l. And now let me raise and lower indices according to my rule. Okay. So first let me replace all the indices by Greek indices. So let's write ij as mu nu. Let's write lambda transpose as lambda transpose mu, since I is the same as this I, which we replaced by mu, and we'll use an index rho over here. Actually, let's use an index alpha, and this would be the same index alpha that shows up here, and let's use the second index of beta, and this would be lambda beta, and j would be nu over here, where I have summed over alpha and beta. Okay, alpha beta goes from 0 to 3. And now let's raise and lower indices appropriately. So let's raise the indices and lower the indices of lambda. So lambda, we should raise the first index, which is put the beta up, and lower nu. And for lambda transpose, if we look at our rule, lambda transpose should have the first index lowered and the second index raised. So lambda transpose mu alpha. Okay. And then we have g alpha beta summation alpha beta is g mu nu. Okay, so now with this rule, what we see is, let's go to our rule of drop the summation or make it implicit. And the way we make it implicit is repeated indices are summed if you have a combination of a raised and a lowered index, okay, which are the same, which means that automatically there's a summation over nu implied in this equation. So similarly over here, we have a raised alpha and a lowered alpha index. So we can drop the summation over alpha and make that implicit. And we have a raised beta and a lowered beta. So again, we can drop the sum over beta. All right. So when we do this, what we get is this lambda transpose mu alpha g alpha beta lambda beta nu is g mu nu. And now what you see is, with this convention, the metric g has two lowered indices. Okay, and this is the defining equation of the Lorentz group in index notation. So now let's look at another equation. So if we take the matrix G inverse, it should be true that G inverse dot G is the identity matrix. Okay, and now we've defined G. So let's first write things with indices without in the standard matrix notation, that is without using Greek letters. So the way we would write this is something like this: G inverse IK G K J sum over K. And now we'll switch over to Greek letters. So we'll write this, the right hand side, as delta mu nu. GKJ we'll write as G nu alpha, and G inverse will be written as G inverse mu alpha. Now what we'd like is for the identity matrix to have one upper and one lower index. And the reason why we'd like that is because if we think about the identity multiplying a vector, this should give back the same vector. And since the vector has an upper index, the identity, which is written as a delta over here, we would like to write it in this form. Okay, where this is a row and this is a column of the identity matrix. And there's an implicit summation over mu, and this should be V nu. Okay, so where the matrix delta is the Kronecker delta, I should have mentioned this earlier, which means that delta nu mu is 1 if nu is equal to mu, and 0 if nu is not equal to mu. So if these indices are different, this is 0. Okay, so this is why we'd want delta to have one upper and one lower index. So let's go ahead and raise the index on delta, the first index on delta. And now, by a rule of requiring the matching of raised and lower indices on the left and right hand sides, we want to raise the index of G inverse as well. So we would have G inverse mu G alpha nu is delta mu nu. There's a summation over not k, but we replaced k by alpha. Okay, and now if we want to drop this implicit summation, we should actually raise the index alpha. Okay, so the index alpha should be raised so that now we have a repeated upper and lower index, and we can drop the implicit summation. So when we do this now, we find that G inverse has both upper indices. Okay, so summarizing a few things, lambda, the transformation matrix lambda, has an upper index and a lower index like this. Vectors have an upper index like this. The matrix lambda transpose has a lower index here and an upper index here. The metric G has two lowered indices, and the metric G inverse has two raised indices. Okay, and whenever we write down an equation, the upper indices on the left side should match the free upper indices, that is the indices which are not summed over on the left side of an equation, should match the free indices on the right side of an equation. Okay, and free upper indices, and the same should be true for the lower indices. Now, these four vectors that we've written in index notation, V mu, these are called contravariant four vectors. That is, if I know the vector V mu in one reference frame, or say in the frame of an observer S, and I want to find V prime mu in the frame S prime, then the transformation rule is V prime mu is lambda mu nu V nu, where I've summed over nu. Okay, this would relate the vector in S prime to the vector in S. Okay, and in the special case, for example, where S prime is is a frame which is moving along the x direction with the velocity v, the matrix lambda is gamma minus gamma beta 0 0 minus gamma beta gamma 0 0 0 0 1 0 0 0 0 1. Okay, so in particular, if I take lambda 0 0, this is gamma, lambda 0 1 would be minus gamma beta, and so on. Okay. And if v were the standard space-time vector, v0 would be ct, v1 would be x, v2 would be y, and v3 would be z. Okay. So this defines the our transformation rules for four vectors. Now, any collection of 4 numbers obviously does not form a 4 vector, but I could imagine taking other combinations of these 4 quantities. And since I know how V0, V1, V2, V3 transform, I would also know how those other combinations transform. So let me construct something here. I'm going to construct a new kind of 4 vector, which is really constructed from the old 4 vector with components V0, V1, V2, and V3. Okay, so the way we're going to construct this 4 vector is we're going to take V mu and we're going to multiply it by the matrix G. Okay, so we're going to take a G dot V. Okay, and we're going to ask, what is this quantity? And let's call this some new quantity. This is still in the frame S. Okay, so everything that we're constructing now, both sides of this equation, this is in frame S. We're not making a Lorentz transformation. We're just asking what this quantity is. So this is also in a new object, which we'll call, let's call it W. This is also in frame S. Okay. So in index notation, V has an upper index, G has lowered indices, and we are summing the raised and lowered indices. So the object W would have a lowered index in this case. Okay, so explicitly the entries of G, so G is this matrix with zeros everywhere else. So G00 is 1, G11 is -1, G22 is -1, G33 is -1, and all other entries of G are 0. So what this is going to do is, supposing I have V0, V1, V2, V3, the components of W for each value of nu would be, W0 would be V0, W1 would be minus V1, W2 would be minus V2, and W3 would be minus V3. Okay. So it's not that I've constructed a new 4 vector, it's just that I've taken the components of the old 4 vector and performed an operation on them. Okay. And I'm still talking about the same 4 vector, but I've just redefined the components of that 4 vector. Now, the transformation law for W is obviously going to be different from the transformation law for V. All right. So let's ask, what is the transformation law for W? So now suppose we go to a frame S prime. We'd like to know what is W prime. Okay. And we know what V prime is. And we know what G will be in the new frame. Okay, so this is known, this is known. The metric G is unchanged, okay, because the space-time interval is unchanged. So the metric G is unchanged in a new reference frame. We know how V prime transforms, and therefore we can derive how W prime would transform. So, so we had W nu is G nu mu V mu. So now if we make a transformation, let's transform both G and V. Okay. So in matrix notation, V would become lambda V and G would just become G. And this would give us our W prime. In index notation, we would write this as G again with lowered indices, nu mu. This is W prime nu. And lambda V would be lambda mu alpha V alpha. Okay. Note again how the raised and lowered indices, repeated indices, are summed over. Okay. So you see that the transformation rule for W looks like this, but we want to write the transformation rule for W not in terms of V, but in terms of the original W. But that's easy to do. Again, if we look at this equation in matrix form, okay, what we can do is we can write this as W prime is equal to, let's stick in factors of lambda transpose and lambda transpose inverse. So this is the identity matrix dot G dot lambda dot V. And now, since matrix multiplication is associative, we can perform this matrix multiplication first. And by the defining property of the Lorentz transformations, this is just G, so I can write this as G times V. And so now we have lambda transpose inverse times GV, which we can write as W. Okay, so the transformation law for W is different from the transformation law for V. Okay, it's not through the matrix lambda, but rather through lambda transpose inverse. And in index notation, we could write this as W prime nu is lambda transpose inverse, whatever this matrix is, we take the nth component and the mu component, W mu. Okay, so this is the law in index notation for the transformation of W. This law is not an independent law, it just comes out from the law of transformation of our regular contravariant 4 vectors.